Hi guys, this is the mini lecture on geological time and the sort of introduction to climate changes over really long time periods. So thinking back to climate forcing mechanisms, we're going to be talking about the tectonic scale of those climate forcing mechanisms. So things that take place over tens of hundreds of millions of years. So, and then to do that, we're going to look at how the continental plates and their arrangement or their geography on the surface of the Earth has changed through the Phanerozoic. And then we'll also talk about the polar position hypothesis. So geological time is covered briefly in the textbook, but things like the polar position hypothesis is not covered in the textbook. So we'll use our notes from our lecture slides to help us sort that out. And so maybe you've seen the diagram that's showing up here on the screen on the right-hand side, looking at sort of our fossil record, and we were just talking about the KT boundary, so the Cretaceous to Tertiary boundary, so big extinction event, even larger extinction event between the Permian and the Triassic boundary that we're looking at here, and then going all the way back to the Proterozoic and Archean. When we look at the right-hand side of this, you'll notice that our time steps aren't equal as we go through this whole time range here. And this is the challenge, is that we have tons of details, well, relatively tons of details for the last sort of 500 million years, or 540 million years, and that's the Phanerozoic. And as we go back further in time, our fossil record is much poorer, and that's because there really wasn't that much life on Earth. It was relatively really simple at that time, and not a ton of fossils that go with it. And just in case you were like, ooh, tell me more, Jackie, the age of the bedrock in and around Guelph is around sort of Ordovician Silurian time. So that's how old the bedrock is around here. But clearly things have been happening here since then. We just don't have bedrock showing up to show us that stuff. I was surprised when things are going to start or not. All right, so this is that idea of that geological time. So if we make all of that time sort of equally spaced, if you look at Earth's history, we have very little, like very few ideas about what actually was happening, right? Going back to 4.6 billion years ago, or 4,600 million years ago, we've got like, this is all we've got in terms of our geological record. So all of the details are really in the Phanerozoic. And so when we're looking at all these things, we're really just looking at a really short time period in Earth's history. So in thinking about these things, this is important to keep in mind. In terms of how that changes over time, and again, we get to see more details as we go through time in that. So through the Paleozoic, Mesozoic, and Cenozoic, we've got much more ideas about what's happening. And again, this little tiny line here at the top, that's us. Like, we are barely a blank in terms of Earth's history. One of the things that you may have seen, and again, we just looked at a couple examples of this, is what do all of these words mean and stuff? So at all of these tables and these time scales, the most recent time is at the top of the picture, and the oldest time is at the bottom. So we have that sort of denoted here on the left side of our diagram here. So this stuff down here at the bottom is super old, and towards the top is the younger stuff. Then we've broken up those different time sections into different names. So eons, so the Hadean, Archean, Proterozoic, and Phanerozoic. So Phanerozoic is us today. And then we can break up those things into smaller time sections. So era, period, and epoch. Sometimes people like to ask lots of questions about this. I'm only interested in, so that I'm using this as a way for you to refer back to, because I'll talk about the end of the Cretaceous, or I'll talk about the Permian, like we've done in the previous little mini lecture. And I just want you to have an idea of when that is in time. So the Permian is older than the Cretaceous, and the Cretaceous is older than today, as that example. And all of that is part of the Phanerozoic, which is really just for 540-ish million years. When we start talking about Earth's more recent climate, we're going to look at the Pleistocene. So that's like this section down here in the epoch. So we'll sort of talk, you'll hear some of these words in the next couple of mini lectures. So in thinking about Earth's climate, and again, remembering how old the Earth is, we need to keep in mind those shifts. So just as a quick sort of reminder, right? So the Phanerozoic, if we break that into eras, we go Paleozoic, Mesozoic, Cenozoic. And if you're into Latin stuff, Zoic more or less means life. Ceno means new, Meso means middle, and Paleo means old. So here we are in the like new or the now life. And if you notice that CEN prefix here becomes the suffix in all of the epochs for the Cenozoic. A weird nerd thing you can show off at the next time we're allowed to actually socially gather and go to a pub night or trivia night. Maybe you can do it online. When we take a look at our time frame here, then this next thing we're going to look at, we're going to be looking at just the Phanerozoic. So you'll see words like Ordovician, or Cambrian, Ordovician, Silurian, Devonian. If you're in the UK, you would say Carboniferous. In North America, we typically say Mississippian and Pennsylvanian. It's broken into two, Permian, and then we move into the Mesozoic, Triassic, Jurassic, Cretaceous. And then the Cenozoic periods are Paleogene, Neogene, and Quaternary. And with respect to the Cenozoic, because we have more details, if you think back to our proxies, we actually divide these periods into other words as well. So Paleocene, Eocene, Oligocene, Miocene, Pleistocene, Pliocene, Pleistocene, and Holocene. And there's cool ways to memorize those words if you're into that. If you find any good ones, share them on CourseLink. I'm not going to ask you to memorize and put down these things again. I just want you to recognize when we start talking about things, when we say Phanerozoic, we mean 540-ish million years. But when we say things like the Pleistocene, it's really in the last couple million years that we're talking about. So thinking about hothouse, icehouse eras, so you'll notice these are the words we were just talking about. So these are the words we were just talking about in that previous slide. So Precambrian, this is like before the Phanerozoic, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, or Mississippian and Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, and Tertiary. So that's those time frames. So our time is on the sort of blacked out left side of these diagrams. And these diagrams are really tall diagrams, so I split it onto our screen in two places. And if the point here that I want us to like eventually get to, I'm getting there, is I want us to see I'm gonna use my spotlight here. I want to show off the, oops, it's not gonna let me do that. See if I can, sorry for the pause. I think I can do it with this pointer here, yeah. So if we've got our starting point down here, down on the bottom right, we're starting at about 10 degrees Celsius. That's the average temperature at the beginning of the Precambrian. As we move from the Precambrian up, and I've now lost my pointer entirely, this is terrible. Let's go back to mouse. All right, as we go back, as we move through time, I'm on the bottom right down here, everybody, sorry. Maybe I'll do it with PowerPoint. Yeah, sort of I've got a laser pointer down here. So as we move through time here, we warm up and then it cools down, and then we warm up as we start the Cambrian. So the Cambrian's pretty warm. If you look back in record, and this line that I'm trying to highlight here, this is our line that's showing us our temperature. So as our temperature increases at the end of the Precambrian and the Cambrian, it's pretty warm. Average temperature on Earth is around 25 degrees Celsius, which is warm, because remember today we're around 16 degrees Celsius is our average temperature. So then as we move through this, Cambrian's really warm, all kinds of vegetation, life's going bananas. We get this abrupt cool period through the end of the Ordovician, beginning of the Silurian. And so it gets really cool, and then it gets really warm again. We go that full range in temperature shifts. And then again, it warms up through the Silurian and Devonian, and then through the Carboniferous, it gets gradually cooler, not as fast of a change as we saw during the Ordovician. And then through the end of the Carboniferous into the Permian towards the Triassic. So I went from over here, we gotta like continue the line down here to the Triassic. We had like, it's gotten quite warm towards the end of the Permian, super warm at the end of Permian. And that's actually part of the reason why we see a mass extinction event, we think, at the end of the Permian to the beginning of the Triassic. And it stays warm throughout the Triassic. There's maybe a little bit of like a mini cooling period here towards the end of the Jurassic, beginning of the Cretaceous. Then it warms up for a long time, and then we get sort of our peak warm at the beginning or early part of the Tertiary, and then it gradually cools down to where we are today. And then if we had the right scale, we would see us upwards of ending in and around here. So again, the point of this is that we're seeing things change in our temperature going from hothouse to icehouse. So again, we started off as that icehouse, got into that hothouse era, briefly icehouse, hothouse, cold, hothouse, stayed in that hothouse for a while, and we're gradually cooling in the last 65 million years or so. And so that's that idea that, you know, climate has been shifting back and forth. And so one of the ways to explain how climate has shifted back and forth, let's see if I can get my mouse back here. It's not wanting to do that. Oh, it's because I'm, sorry. Okay, back to my mouse, clear this. Sorry about the delay. Okay. All right, so now looking at that last 540-ish million years, one of the hypotheses was that the large land masses over polar regions of the planet, either the North Pole or the South Pole, were were coincident with mass glaciation. So those icehouse eras only happened when we had ice over the poles. And so this became known as the polar position hypothesis. So this is not in the textbook, so I'm going to say this one more time. So the polar position hypothesis, this is the idea that we had those really cool icehouse episodes that we were just talking about were always coincident when we had land masses over the poles. And that's because when we had land masses over the poles, then we get snow and we get ice, and that has that sort of impact of like reflecting incoming solar radiation, and actually can drive overall global cooling on a planet at a given time. So one way to test this hypothesis is to go back and look at the geography. Where were the continents at what time throughout the Phanerozoic, and say, was that an ice house or not? That's the way we're going to evaluate that hypothesis. So when we look back through different episodes of the Phanerozoic, so 420 million years ago, 390 million years ago, 350, 260 million years ago, we can see at each of those times there's land mass over the South Pole in each of those cases. So there's a project called the PaleoMap project, where someone has gone through and reconstructed where each continent was and what things were like at that time. So I'm going to flip through these quickly because we don't need to memorize any of this stuff, but just to kind of give us a sense of what things were like at a given period and whether or not we had landmass and ice, evidence of ice at the poles. So this is the beginning of the Cambrian period, so very beginning of the Phanerozoic, and we don't know all of the details at this spot, but it was probably not very hot and probably not very cold. So it's kind of somewhere in the middle. And at that time, there was no evidence of ice at the poles. As we sort of move forward through time, so 480 million years ago, we had a relatively mild climate for most of the planet. Continents were flooded by oceans, sort of creating these warm, broad tropical seaways. Kind of think Mediterranean is sort of what you should be thinking about in terms of that climate. And in the top right-hand side of our slides here, you'll see that we have sort of some a legend to what each of these symbols mean. And you might notice that like some of these land masses, like this one here that they've got outlined, they're showing us our present day North American outline. But at the time, like there was no Hudson Bay. This whole piece here was one landmass. We start to get ice sheets forming over the South Pole about 440 million years ago, so towards the end of the Ordovician. And by that point, and again, if you go back to that ice house, hothouse slide, you'll see that we had that really cold snap, to speak. We went really cold really quickly towards the end of the Ordovician. By the end of the Devonian, we start to see Pangaea, which is that major continent, getting together. So that's about 360 million years ago. And again, that's this massive landmass. And you can imagine if we had all of our land masses in one spot, all our continents in one spot, what that would do to our global ocean circulation and our atmospheric circulation as well. So weather and climate are going to be different during the Devonian. At the beginning of the Permian, we had southern hemisphere was covered in ice, and we had a ton of landmass there at that time, and it was quite cold 280 million years ago. But remember, as we got towards the end of the Permian, it was crazy hot, and that's what led to that Permian extinction. Now we're into the beginning part of the Triassic. The middle of Pangaea was really hot and dry, and that might be because of sort of the monsoon type climates that we might have seen at that time. And we also, again, have that idea that we know from the fossil record that it was very hot at the end of the Permian, and it might have created like a super hothouse at that time. Then towards the end of the Jurassic, global climate change began to change again because Pangaea starts to break up. During the early Cretaceous, maybe a little bit of an ice house, like a mini ice house at that time. And then during the end of the Cretaceous, we see massive amounts of global climate that was warmer than today, no ice at the poles. We probably have evidence to suggest that dinosaurs migrated between warm temperate and cool temperate zones over a given sort of a year in that time period. Towards the Eocene, and again, we've gotten rid of the dinosaurs, mammals are just starting to get started. One of the things we can see here is it's starting 55 million years ago. The geography of the planet is starting to kind of look like what we see today. It's not quite what we see today because the Atlantic Ocean is actually pretty small compared to what we see today. And we just are starting to see the split between the Antarctic Peninsula and the southern part of South America. And the Indian subcontinent is just starting to connect with the southern part of Asia. We don't see that sort of definition of islands that we typically see today. By about 23 million years ago to about 5 million years ago, again, the geography is starting to look more like what we see today. And the climate was similar today, but a little bit warmer. In particular, in the Miocene, there was no ice anywhere. So even though we have this idea that if you have land masses at the poles, you should have ice, in the Miocene, we didn't see any ice at the poles. So again, coming back to that polar position hypothesis and considering the history of glaciations and continents, since about 540 million years ago, we know what our ice house eras were, and we know kind of what continents look like in different places. So again, we can evaluate through that, those time frames and our hypothesis to decide, does it match or not match over a given time period? And as it turns out, it doesn't always work. So sometimes it does, and sometimes it doesn't. So only some explanations or cold house eras or ice house eras actually line up with that hypothesis. And so this led to scientists going after other ideas or other theories because it works sometimes, but it doesn't work all the time. So now we need to think about what might be the cause of that change when we didn't have, it was cold, but we didn't necessarily have land masses over the poles, or we had land masses over the poles and it wasn't cold. So trying to figure out that sort of a little bit of that paradox piece. So this is to summarize how geological timescales work. And again, rather than saying 400 or 546 million years ago, we would say at the beginning of the Cambrian or at the beginning of the Phanerozoic. We also got a sort of a super quick tour of what climate looked like in terms of big changes or swings in temperature on the planet. So going from an average of about 10 or 12 degrees Celsius all the way up to 25 degrees Celsius. And then we also dug into the polar position hypothesis, and does it explain big swings in the average global temperatures and climate? And the answer is sometimes, which means that we need another hypothesis, or maybe it's something else that works in conjunction with the polar position hypothesis to help us explain that. So to leave this on a cliffhanger, we'll solve that, what might be the other hypothesis in the next video. I hope you're all staying well. Take care.